Hello. Welcome to the second of our webinar series. It's about 1 minute before it begins, so just clicked over 9 here. So yes, thanks for attending. I think most of you are probably familiar from last week. I am going to be a minor participant on this one. Grant Weaver will be running the show, so I'll go ahead and turn it over to him. Have at it, Grant.
All right. Well, let's give everybody, what do you think? A minute or two here to sign in. People are signing in right now. And as you sign in, of course, welcome. And what's the deal, Nick? If you sign in and your name appears, then you know who it is. But if there's others, they need to in the chat page. Is that how it works?
Yes. So we get a recording of the chat with the meeting, and then we line those up for CEU submission.
So they need to put in the chat regardless.
No, only if they're not signed in as themselves. So if you're by yourself but you're signed in as a city of Baldwin City or something, then make sure we have your the name of the operator there. And if you're signed in and 3 or 4 people are watching, make sure that we have everybody's name there.
All right, great. All right, I'll give it 1 more minute, then I'll start this journey here and see where it takes us. I may be running the show, but I'm relying upon Nick and Ryan to make this thing as good as we can. So get them both in the wings. They'll be playing a big role. Yep, people are continuing to sign in, but I think we're 2 minutes after. That's enough. All right, let's start. All right, I am Grant Weaver, and thank you for joining us. This is the second of 5 webinars. We had one last week. Nick did a great job introducing the whole series and doing a flyover review for the flyover state of all the issues that we want to talk about in this 5-part series. Today, we're mostly going to talk about case studies. I don't know how many treatment plants we have lined up here, and if time permits, 6 or 7 different treatment plants. Folks that have, take the old adage, they drunk the Kool-Aid. Folks that have applied themselves, taken some of the experience Nick and Ryan and I have had from visiting treatment plants, a little tech transfer, and applied it to their own plants, and seen some results. Now, in discussing it, I think we're going to talk about some of the bumps in the road too. So we're going to try to give as honest feedback as possible on some of the experiences out there. Next week, we take the week off. That's Thanksgiving Eve. So who wants to do this on Thanksgiving Eve, even though it's free credits? So we're going to take next week off. And then the week after, dive in pretty deep to nitrogen removal. Part of that, I'm sure, for most everybody will be review, but hopefully that'll be of interest. Nitrogen is real important, even if you're really more concerned about phosphorus. There's a lot in nitrogen removal that, if it's not done well, can interfere with your phosphorus removal. So we'll do nitrogen, and we'll do phosphorus, and then we'll close it out as we're starting to get awful close to Christmas here on December 13th. All of these the same time, same place, 9 to 10:30 on Wednesday mornings. Close it out with a review, and the more discussion, the better throughout this whole series. So I know it's intimidating, but through the chat or even unmute yourself at any time, I think Brian and Nick and I are all very comfortable with being interrupted with comments or questions. we want to make sure everybody gets the credits for this. It's wonderful that the state is providing the service and allowing you to get credits without, by just participating from your place of work. So with that, Ryan, if you're ready, come out of the green room and step forward, and we'll start with Ryan. I'll mute myself and just be the guy who advances the slides here for a moment.
All right, thanks, Grant. Good morning, everybody. For those of you who don't know me, I'm Ryan Eldridge, the unit chief for municipal permitting and engineering at KDHE. So we're the unit that issues the permits for municipal and commercial facilities. So I guess you could, call me the bad guy when implementing these nutrient limits in your permits. A little background on me. I have 5 years of operating experience. So through college at South Dakota State, I was an operator at the Brookings wastewater treatment plant. Kind of had a cool assistantship program there where the students ran the plant on the off hours and weekends and gave the full-time guys off for that and holidays. I have a civil and environmental engineering degree from South Dakota State, registered PE in Kansas, and a class 2 wastewater operator in Kansas and South Dakota. There you go. So a little background on kind of nutrients in Kansas. So in 2004, KDHE came out with their kind of nutrient reduction strategy, which was to address excessive nutrients in state waters through load reductions from non-point and point sources. The goal was to reduce about 30% of nutrient load leaving the state. That's both from non-point and point source. Today, we're mainly, focusing on the point source with you guys as wastewater treatment plants. About 85% of the wastewater load is from plants greater than 1 MGD kind of design capacity in the state. Some updates. We are working on kind of a nutrient vision 2.0 strategy in the coming years, but as far as you guys are all, I guess, should know, we still believe this kind of approach of the, the nutrient goals and as well as the loading limits, based on an annual average is kind of the approach versus numeric nutrient criteria. Next slide, Grant. So here's kind of how we implement these. We started with kind of the 8, 1.5 goals, kind of got a little pushback from the consultant and, operation community. And then that's where we kind of moved to the 10 milligram per liter total nitrogen and 1 milligram per liter total phosphorus goals. And, as we implement those, most mechanical plants have those as goals right now. And we are slowly, moving into limits based on loads of those concentrations, which is, your permitted design capacity times 1 times 8.34 expressed as a load. And then that's a 12-month rolling average. Next slide, Grant. Oh, there we go. So to assist the state, or not states, the municipalities and cities, we have kind of invested heavy in optimization. This kind of started in 2011 with a contract with Fort Scott Community College and Jerry Grant. I know he went out to a lot of plants I think his main focus was on nitrogen removal, and he visited quite a few plants across the state, and they really got good at nitrogen removal. Then in 2019, we kind of ramped it up a little further, bringing Grant on board through Fort Scott as well, sending him out to almost every larger mechanical and small mechanical plant in the state. Also doing, on-site training as well as, classroom training for operators across the state. And then in July of last year, we kind of moved Grant under contract with Wichita State and Nick Willis, kind of provide Grant's more kind of the behind the scenes, that remote support where Nick is more the boots on the ground, can kind of go out and be the person in the state and visit these facilities a lot easier and cheaper for us. And all this optimization training and stuff is, free of charge. It's funded by our state revolving loan fund, kind of the service fees and stuff like that. So it's all free of charge for you guys. And we encourage you guys to use it as much as you guys need and want. So here's kind of just some output measures, and as you can see, just based on the graph, the training's been paying off over the past 5 years. You can see the large increase from 31 wastewater treatment plants back in 2017, kind of meeting those nutrient goals or all the way up to 67 as of last year. And I guess for reference, Kansas has about 100 and 10 or so mechanical wastewater treatment plants in the state. So we're kind of right around that, a little over 50% meeting those nutrient goals. Kind of here's just the state overall median. So see total nitrogen, we have at least over half, meeting that total nitrogen goal of 10 milligrams per liter at that 8.1. Phosphorus, it's a little more challenging, that median's right around 2. But this definitely, due to the results of construction of BNR as well as optimization of existing wastewater treatment facilities. And, I guess a caveat with these, I expect these numbers to go down further in the next, 5 years as a lot of older and larger mechanical plants being upgraded currently, as well as, the continued optimization efforts with Grant and Nick across the state. So I expect these numbers to drive even further down as the years come on. And here's kind of the final slide, just, kind of proving optimization is working. This is kind of the percentage over kind of when we started this full-blown, optimization efforts with Grant and then Nick on board. And as you can see, most of the categories we're getting better as the years come on. Nitrogen, there's a little slip from 20 to 21, but then it jumps back up. This is a lot of this credit is due to the operators taking this training and definitely applying it to their plant. So I definitely, kudos to you guys, because you guys are the ones that at the end of the day make this happen. We can provide the training and stuff like that, but that doesn't do it alone itself. It's definitely you guys implementing the nutrient removal, the training, and taking what you're learning and definitely applying it to your facilities. So we definitely, commend all you operators for that.
All right, I think that's my cue. I will share my screen. It's okay. Okay, so I think I've met probably well over half of the people on the call. I've been with the Environmental Finance Center for just over 9 years now. Ryan missed one thing in the history there, that we had a contract for 4 or 5 years with KDHE for jar testing. So myself and my late former boss, Michelle Pugh, went to something like 50 some plants in the state for jar testing for chemical phosphorus removal. And we learned a lot from that. The primary learning is that you probably want to avoid chemical addition if at all possible, just due to cost. Most facilities were in the $3, $4, $5 per sewer connection per month for chemical costs based upon the jar testing. So pretty significant rate increases would be needed just to pay for the chemical, not to mention any of the other further things. Prior to that, I was at the city of Page, Kansas, in their water and wastewater utilities. And then I've been kind of in Ryan's role, though not as high in the organization. That was my first job out of college, writing NPDES permits. And I do have a biosystems engineering degree, and I'm a registered PE in Kansas. I'm going to talk about some of the case studies. So this is one, the city of Harrington, their plant here is on the right, kind of the heart of their plant. And I'll turn on my laser pointer here. This is an activated sludge treatment facility. There's 4 parallel basins here. The RAS and influent come in here, and then they split off. So this facility is pretty limited. Quite old activated sludge facility. They are kind of in line for upgrades, and I think both the city and I knew that we weren't going to get 10-in-1 total nitrogen and total phosphorus from this work, but we wanted to experiment a little bit. And also the city had a brand new operator, Jason Alt, who was real eager to learn. He'd been in the water treatment side, so kind of had a good background for it. They were eager to learn what the plant could do, and to help inform what are some potentials at the facility as we're replacing blowers and control systems. So they're kind of doing new headworks, new aerators, and new blowers at this facility. And they're in pretty desperate need of all of these. All of this equipment is at the end of its life. And then again, we have those 4 parallel basins. So we did some limited trials in Harrington. We knew that their system had plenty of air. Their dissolved oxygen was often 4 or 5, 7, 8 milligrams per liter. So backing off the air in some locations probably would not cause very many problems with regard to compliance with ammonia. So one of the questions we wanted to answer was, can we lower the nitrates at this facility with the limitations in hand? So we were unable to, have a dedicated recycle stream to a dedicated anoxic zone at the plant. Jason was also not comfortable with cycling the blowers due to, they're like 20 years old or something like that. Due to the stress on them, didn't want to have any significant repairs before the new one comes in. So he's trying to limp them along until new equipment is installed. And I totally get that. And I if I were in his place, I'd probably do the same thing. So given those limitations, we're going to try to reduce the nitrates a little bit. So how do we do that? At pretty much every plant, if you have high nitrate levels, you're also going to have high nitrates in your return activated sludge. So here's one of the 4 basins, and then there's another on the left, and then 2 more on the right. So water comes in near where I took the photo. No, actually the other way around. This is near the overflow. So we wanted to see what we could do given the limitations of the plant as it is. Jason indicated that the return activated sludge is typically about 40% of the plant influent flows. So a lot of the nitrates that are generated in the plant from the ammonia conversion are coming back to the splitter box out where my laser pointer is. So what, that's a source of nitrates. That's a potential place we can reduce those nitrates. So what we did is that we turned off the aerator, the first aerator in 2 of the basins. The theory being that we have lots of food there, that influent BOD for the denitrification, and then we have the nitrates there. So can we form an anoxic zone given the limitations at the plant? So what we did was that I had some loaner equipment, and Jason began monitoring the nitrates coming out of these basins. What were the results? We saw that we were able to remove about 2 to 3 milligrams of nitrates in the modified basins. So, not a drastic change, but, the plant often was putting out, 11, 12, 13, 14 milligrams per liter for their monthly average. So that would get them to 10 or most of the way to 10. And I certainly feel that we're pretty comfortable to be able to meet the 10 once we have some more flexible equipment situation in place. We also saw no ammonia increase, which was expected, and it's always good to see that be in place. So takeaways from Harrington here: not wonderful, the city didn't save $6 million on a new plant, but we did learn a lot. First, and this is one reason why KDHE wanted Grant and I to do this work, these webinars, is that new operators are coming in, all the time at facilities. So with a new operator, that is a time to kind of change the old mindset of, we have an activated sludge plant, we remove ammonia, we remove BOD, we remove TSS, and we disinfect, and we're good. That's not the reality anymore. So as a new operator is coming on board, having education such as this, or me visiting, can be very beneficial, and I think Jason hopefully he benefited from that. So he gained that education and experience. I think I'm also pretty comfortable in saying that they should be able to meet 10 milligrams per liter total nitrogen with upgrades. They'll be able to cycle, they'll be able to control DO levels. So I'm pretty comfortable there. And also, I think that if you are on the border with total nitrogen discharge levels, that even given a situation where there's quite a few limitations in the modifications you can make in your operation, you may be able to move the needle. You don't have to have full denitrification to meet that 10 milligrams per liter. Just some of it has to denitrify. We're now going to move to a new build plant, which was Horton, and I covered this last time. So they have a new Aeromod facility, and the picture here, they have kind of anaerobic zones. This first little zone on the south side, and then this larger zone. RAS comes in from the clarifiers at the Aeromods. If you're familiar with the facility, this will make sense to you. To bring in the biology. I believe this first little anaerobic zone does not have any RAS, so it's just influent that's kind of allowed to sit and rot, for lack of a better word. So they weren't getting very good phosphorus removal. It wasn't terrible, but it wasn't kind of meeting that 1 milligram per liter goal. This plant has a nutrient limitation coming in a year or two. And the plant was built with chemical feed, but the operator certainly does not want to use it if they don't have to there. So what we did, I have some loaner equipment for oxidation reduction potential. I just lint it and then had it log on a 24-hour basis. So throughout the day, what is the ORP in, I believe it was this basin that was sampled. So we were gathering data to try and diagnose the problem. We saw that the ORP was really kind of in an anoxic zone. So you would expect denitrification to occur, but not that fermentation and the VFA uptake by the biology that does the electrophosphorus uptake later. So kind of on a just best guess, we reduced the mixing there. The mixer was programmed into the SCADA system. It's a new plant, so good job on that integration. And we just had the mixer turn on and off on an hourly basis. So 1 hour on, 1 hour off. The goals of this work was compliance with total phosphorus limit when it comes online. Definitely avoiding chemical addition just from a cost basis. City has a brand new plant. They have to repay the loan there. So they're trying to run as cost efficiently as possible. So here's what we have on the concentration limits. So here on the left is kind of before we modified the mixer, and then you see the values come down. Now we're not under 1 on a concentration basis, and we also saw a spike here, and we're going to keep an eye on this, whether this is a one-time deal or something else is going on. We'll have to see, but keeping in mind the permit limit is going to be on a pounds per day basis. The future limit, if I have it right, is 2.07 pounds per day. And this is, the monthly average here. They're in full compliance, with the exception of maybe this late September data point, even though they were over that 1 milligram per liter. So, it's the concentration times flow times the 8.34 is really kind of the bottom line for compliance at Horton. So in the future, they hope to monitor ORP more. They may need to do some other things too. If they have, if it's not just a fluke that they had a high phosphorus value, they may need to better monitor nitrates going into the anaerobic zone through the RAS. They may not be getting good enough denitrification to protect this area. The VFA might be consumed by denitrification. They may also need to better control the nitrates in the cycling of the Aeromod basins to basically reduce the RAS. They might also have something going on with their biosolids processing. So phosphorus does not go to the air like total nitrogen does if you remove it. So they may be having some internal recycling there. So, it's an ongoing journey. New plant, there's a lot to learn in its ins and outs. And both Grant and I are fully able to support them in that effort if need be going forward. My final case study is Concordia. So Concordia is interesting, and their plant's way too big for their community. So one takeaway, and you'll see this at other facilities as well, that we profile here, is right sizing of the basin. So just because you have a basin doesn't mean it is beneficial to plant operations to have it online. So show you a little bit what Concordia did there. Concordia also has very good control of their air input, and they have very consistent nitrogen and phosphorus performance at their facility. So what did they do to right-size their tank? Concordia population has fallen quite a bit since the plant was built. So their flows are much lower than their design. And most plants, I believe theirs was built, sometime in the 80s. Most plants in that era were built with population growth in mind. And most of the state of Kansas has not seen significant population growth. So there's a lot of both water and wastewater facilities out there that are probably oversized given the community size. So at a bottom line, their plant's really too big. It leads to old sludge and other related problems. So you'll see here that the middle basin is dry. So they're operating probably a little more than 2/3 of the plant volume here. They also have a clarifier offline. So they're operating on a single clarifier. They also operate at very low mid-slicker concentrations. In the summertime, somewhere in the 1,500 to 2,000 milligrams per liter. And if anybody at Concordia is online, feel free to correct me on this. So another way to make a plant smaller is to run a thinner mid-slicker. So you have less biology there, given the size. So fewer pounds of biology are in the tanks. And that helps deal with some of the hydraulic limitations. The controls at this facility are done with an ORP meter that controls the air in the basins. This allows them, given kind of the carousel nature of this, to have various environments within the plant, even without kind of like baffles or hard walls and separate basins. They're able to create aerobic, anoxic, and anaerobic zones, and they meet expected mass limits. So I'll show you a few of this. This is from EPA. This is their total nitrogen in their effluent. And I mean, this is just wonderful. The top number here is 10, going back to mid 2020. So they're often putting out less than 2 milligrams per liter total nitrogen. And that's probably about as good as any plant in the state does. Our total phosphorus is a little less consistent. Again, and they have the limitations of their plant. They're optimizing it given what they have. And you see really good phosphorus levels, well under 1 milligram per liter some months. And in recent months, they've been quite a bit higher. It's my understanding they're putting new biosolids processing in. And that would be my expectation that the plant, with the new biosolids, they probably had some built up and they've been doing extra processing since then. So I would take this with some grain of salt, these recent high values, as they get their new system online. But overall, they're meeting their mass-based limits if and when they do come with this. Keep in mind, from a optimization point of view, they have created a plant that looks like either the top or bottom, without any of these hard separations. And they're not the only plant in Kansas to have done that. But they certainly, I don't think there's a plant that's doing better on total nitrogen optimization than Concordia. And on total phosphorus, they do about as well as I would expect, given the limitations they have, with kind of a lack of baffling or separate basins. With that, going to turn it back over to Grant. And as we do that, I think there were a couple chat. Oh, okay. Yes. Nick, the plant is in Horton. Grant, have you? There you go.
I'm working on it. Let me. You know
right.
what? I think because I got to advance right through all of yours. Otherwise, I'll get off.
Yes. See it again.
Bear with us here. Here's a repeat. This is speed reading here. All right, we're in Concordia now, finally. All right, that looks like me. All right, Nick, thank you. Thank you, Nick. Thank you, Ryan. We're a third of the way through here. I look at my clock almost exactly, so we got about an hour to go. I'll introduce myself and then want to kind of jump shift into another topic, and then we'll get back into the case studies. So as I mentioned last week, I grew up in Wichita, went to Wichita East High School, went to Kansas State, and then from Kansas State down to Oklahoma State. Oklahoma State studied, really got into, they actually have a graduate program there in wastewater treatment. I just loved it. My senior year in college, I took a class on wastewater treatment, and even though I was really a lousy student, that's a class I excelled at, and my professor helped me get into grad school. And then from there, moved out east, and you know, the world falls apart. You become an Easterner and find an Eastern woman and get married and have kids, and here we are. So I'm a professional engineer and an operator. I graduated from college in '73, so I've been doing this a long time. And what happened was 25 years ago, I started a business running little treatment plants, and here in Connecticut, they had nitrogen limits on them. And these plants I started running weren't meeting their nitrogen limits, so I had to learn about it. And how do you learn? You learn but through trial and error and through research and making mistakes and getting some things right. And then I started bringing that experience to bigger plants. And then as nitrogen pretty much kind of like the story Ryan just told, started out with Jerry Crant with the nitrogen. And then we actually learned a lot more, we in the field in the last 10 years, maybe 15 years on phosphorus. And now I have a lot better understanding of that. So applied that to phosphorus removal as well. All right, we mentioned last week that I tell you, this is a pet idea of mine, so I'll take the blame for it, pushing it. I think it'd be really nice to set up some kind of a cohort where initially anyway, Nick and I we'll bust it into groups. Get a group of Aeromod operators, for example, around the state of Kansas, and have a call every couple months and kind of talk about what's working, what's not, get operators talking to operators. When I give training in class, in the classroom, boy, the most rewarding thing for me is when operators start talking back and forth. We live too much in our little silos, I think, as operators, and don't get out and benefit from what other people are doing right or lessons they've learned by doing them wrong. So the idea is if we could set up an hour and a half, 2-hour call, have a video chat, kind of like this, but less formal, even though we want this to be as informal as possible. And with time, it'd be kind of like a lunch chat, I guess, between operators would be the idea. So that's the concept. And we're going to do a little polling question here and see if there's an interest. And if there is an interest, we'll flesh it out here in the remaining, 3 more webinars. There it is. So yeah, put that right up there. There's the polling question. So why don't you all take a moment and vote? And don't vote one way or another to try to please anybody. Let's be honest, we don't want to waste people's time trying to set this up if there's not a lot of interest. But if there is, the state's been very responsive to the idea, KDHE, of supporting us in setting it up. So please take a vote. We'll tally the responses here, give you a minute or so to vote. And I guess if there's a bunch of you in the room, whoever's the biggest, baddest, loudest person gets to choose how you vote on it. Or maybe whoever's got the highest ranking. I guess that would be the way it would go. Nick, are they coming in? Tell me when you've got them in. And
yeah, we have about 52 out of 80. There's 3 of us here who won't vote. There might be some people who aren't, operators at a Kansas plant, or, I think Iola is on the line. We're not doing lagoon optimization quite yet here. So
okay.
I'm going to go ahead and end the poll in just a couple seconds here. So go ahead and click if you want to. All right. So Grant, you may not be able to see it.
I can. Yeah.
20, okay. Yeah. 26 people said yes. 18 said maybe I need to know more. There were 9 no's. And then 2 people said they would delegate it to somebody else at their plant. So we'll take these results, have a look at them, compare them to the technologies here, and see if we have an obvious first cohort. And if you're really gung ho about this, feel free to contact me or Grant by email, and we can see what we can do.
Yeah, and then the timing on this, I think we've talked, Nick, would be after the new year sometime, right?
Yeah. Yep. Okay, back to you, Grant.
All right, so we voted. I'm going to share a little bit about my experiences, and then while Nick was going through the case studies, I was furiously writing away because I thought there was a really nice storyline. And but first, let me share kind of what experiences I've had. Nick's are pretty extraordinary experiences. I don't know how many dozens or over 100 treatment plants at this point Nick has supported. As he told us, just for the chemical phosphorus removal, I forgot that number, 50, 60, 70 plants around the state. And then Nick and I have traveled together to many in Kansas. But around the country and even up into Canada, here's been my experience the last 15 years in plants, going to facilities around the country, trying to play the Johnny Appleseed role here of promoting this idea of optimization, and then leaving it up to operators to take the information and run with it, or not, or modify it, or improve it, or whatever. So few in Canada, Connecticut, that's where I live now. Iowa, the last 2 years have been doing tours of Iowa. Any of you are familiar with Iowa has the annual bicycle ride, the RAGBRAI, goes from the Missouri River to the Mississippi River. This is, we're doing a wastewater tour across the state, sponsored by the University of Iowa. So we go the other way. We go from the Mississippi to the Missouri River. Kansas, 73 plants. I've had the pleasure of visiting, and I'll give you all of that detail here in a moment. 1 in Kentucky, 13 in Massachusetts, 3 in Minnesota, that's been a real interesting experience. Got some very small plants that have pretty significant interest in working on optimization. One has dropped both the nitrogen and phosphorus so much that they're pretty much canning the idea of abandoning their little treatment plant for their population of 300 people, has a mechanical treatment plant, and was going to abandon that and go with a lagoon. But they're getting the numbers now, so why build a lagoon when they're getting the numbers? Montana, like Kansas, in fact, was the first place state that embraced this optimization effort and gave me the opportunity to cut my teeth starting in 2012. Visited pretty much maybe 1 or 2 mechanical plants in the state I haven't visited over the last 10 years, at least once. And Montana, let me tell you, it's a big place. It can be a long ways between treatment plants some days. New Hampshire, North Carolina, North Dakota, South Carolina. Tennessee's another state like Kansas and Montana and Iowa that have really embraced this from a regulatory standpoint and are supporting it. In fact, we're looking, Tennessee is looking to do 24 treatment plants a year and multiple visits. And Tennessee has like 200 mechanical treatment plants. So they're on track to try to provide free optimization support. Virginia won. State of Washington, that was very interesting. That was actually funded by a electric utility. And their thinking there was, as Nick was talking about that Harrington case study and turning some of the air headers off, even though I guess that blower didn't have a lot of controls, the idea this electric utility up in Washington was excited about was Puget Sound has new nitrogen limits, and to meet them, they figure a lot of facilities should be able to reduce their electrical demand as they start shutting off some of the aeration equipment. It's a fun project working with that. Had a real good success, which I think is going to appear in the next month or two in TPO magazine. That would be Lake Stevens. So keep your eyes out for that one. Pretty nice story. And then Laramie, Wyoming. Total 193 plants around the country. Here they are. And you can see Kansas takes up a good chunk of that page. And I would say that at least half of those under Kansas, both Ryan and Nick has been to it as well. And I know that in both their cases, they've been to facilities that I haven't been. So the technical support opportunities there in Kansas. And I want to, after I do this next slide, I want to speak to that whole storyline that I picked up during Nick's presentation. So I just got to do this. This was so much fun to do. So here's the 73 plants in Kansas in alphabetical order that I've had the opportunity to visit in the last 15 years. Many of whom have embraced this idea of changing the way their plants operate to give those numbers that Ryan was sharing earlier. So pretty much peppered all over the state. Like I said, Nick, Ryan, and I have, in some combination, often all three of us have visited many of these facilities. It's really helpful to have, a brainstorming effort and to have that regulatory support from the state. So here's a storyline that I wrote down while Nick was talking. So we visit a treatment plant. And then based on our experience, and you can see, not that we're geniuses, but we've just been to a lot of facilities. And so we've been to a lot of, I did a count of oxidation ditches, because this year in Iowa, did 9 oxidation ditches. Been to 40 oxidation ditches. So a lot of experience. So based on that experience, kind of a tech transfer. Okay, you've got an oxidation ditch to improve nitrogen and phosphorus. Here's what I've seen, we've seen in other facilities, and brainstorm ideas. And then you, the operators who know your plant, say, well, we tried that, and here's a problem with it, or we didn't try that, or here's what's in the way of that, or here's another way of getting to that. If you engage, then you can take that kind of broad level experience and bring it right into your plant, and then we can brainstorm together. Okay, based on that, come up with a little bit more detailed strategy, just as Nick showed in his examples. And then operator preference. Well, I don't really want to cycle my blowers on or off, or yes, I'm comfortable cycling my blowers on and off. And we go down whichever path and take it to the end, working together with a strategy. And I think really important, really key is particularly Nick can be in state and he can make a return visit to the plant. For me, I can, and the state will support that, but I can't do it a lot because I got to fly all the way from Connecticut. So we do in plant, we do remote, and as Nick mentioned, he can loan some equipment to do some monitoring, because data, collecting it, analyzing it, and then some of these, as we'll talk about in the next couple webinars, just nitrogen and phosphorus. I like to say it's counterintuitive. You would think to get better treatment, you need more air, and sometimes you need less air. Other times you need more air. Sometimes you need less mixing. So some things that are, kind of unsettling when you're first learning. And of course, as you're first learning and it's unsettling, you're going to put your foot on just like driving, you're going to put your foot on the accelerator when you really ought to be letting off. And so we're there to support that. And then the state is not only there, they're paying for it. And the state, I think, as you heard in that very first session from the top dog, said, we're okay if you make a mistake, not a cataclysmic mistake, but if you actually poke into above your permit limits while you're going for the long game to make for a better operation, you're going to see support there. So where does it all end? We're in sometimes, as I'll be showing in my first case study in Great Bend, it shows don't need a facility upgrade anymore. $6 million that we thought we needed to spend, don't need to spend. Not always going to end up with that cheery of a story, but even if it doesn't, and you're learning in advance of a facility upgrade, it's going to empower you as an operator to feel more comfortable and to be more respected and to have a stronger seat at the table and get a better solution. There you go. That's the story I heard from my notes here that as Nick gave his presentation. So that was a big wind up to the pitch. We're here, and the state has given us a pretty generous budget to spend time to provide assistance. And the assistance, as I just mentioned, I'll repeat myself, can be in plant, can be providing loaner equipment, can certainly be a lot of remote telephone, email, do video calls, whatever works best. So if you're just suggestion, maybe you want to hit your print screen on this one and just print, and then let's keep this, and then you have Nick's contact and my contact, our phone numbers, our emails, and you can reach out to us anytime. So if you hit print screen, then later just paste that into a blank Word page and print that, then you'll have that. We'd enjoy hearing from you, and we'll probably reach out to many of you anyway, even without hearing from you. All right. back on track. Let's do Great Bend. Great story. This is pretty much a poster child for the optimization effort in Kansas. No, it's not down to 2 milligrams per liter total nitrogen like Concordia. That is truly a remarkable number. There's very few plants I've been to that have that kind of number. And there are a few, but not many. Okay, so Great Bend, I got to give credit to the people. That's the other theme here. The theme is you're going to see a lot of different technologies throughout this webinar series. This is an oxidation ditch facility. Concordia was an oxidation ditch facility. I've got an SBR that I want to use as a case study. I've got a couple other technologies. But it's the people, and it's as much as the technology, and it's developing the habitats for that I'll be talking about in the following 2 sessions for nitrogen removal and phosphorus removal. But if the people aren't engaged at the treatment plant, then the optimization is not going to happen. In the case of Great Bend, both the downtown people, the upper management, Ruben Martin and Jason Cawley were very supportive. They found some funds, they supported it, they encouraged their staff. And their lab technician, April Batt, did a whole bunch of extra testing. And then James Gaunt, who was really the operator, who did most of the intensive work to bring this about. They all 4 deserve the credit for what happened in Great Bend. A nice write-up in TPO magazine a couple years back. If you go to tpomag.com and put in the little search Great Bend, you'll find the story. It's an interesting story. So let's talk about the treatment plant. So Great Bend used to have trickling filters, used to have primary clarifiers. All of that's taken offline. You'll see that in some of these aerial views of treatment plants. You'll see tankage that was abandoned. Oxidation ditches were built, and just like Nick said, Great Bend was going to have this oil boom, mining boom, oil extraction, and it didn't happen. The population boom didn't happen, so the plant's oversized. So Great Bend's running half of the plant. And in a nutshell, there's a headworks, and then the influent and the return sludge will come into this basin, which is an anoxic basin, somewhere around here. There's a mixer here. The flow goes, there's a channel. You can actually see it if your screen's big enough. There's a little space there. There's a channel. The flow goes through that channel. So there's no aeration, just mixing in here. Goes into the main ditch, the racetrack. This is an aerator, vertical shaft aerator. Kind of the end of it looks kind of like a router blade. And it spins, and as it spins, splashes water, and then aerates it, and then also moves it horizontally in a racetrack fashion. As it goes around and around, goes around pretty good lick. I mean, like a walking speed. There's a gate over here. The gate's really like a door, and it is not watertight. It's like a door, huge door, like 15, 18 feet tall door, metal door. And you can open or close that door. When you close it, it's not watertight. And depending upon how open or closed that door is, that determines how much of this flow that's going around and around finds its way back into this zone. So it's designed to remove ammonia, BOD and ammonia in the main body of the ditch, so it's aerobic. And then in this zone, this is designed to be an anoxic zone. This would take the nitrates, just as that first zone in Harrington that Nick talked about, would remove the nitrates. Then the flow goes around, and then every gallon that comes in is influenced, got to displace it, and the overflow is right here, which goes to the secondary clarifiers. So that's the design strategy, the design concept. aeration, ammonia removal in the main body of the ditch, and nitrate, excuse me, removal in the anoxic zone, not designed for phosphorus removal. The aeration equipment on this was originally 2-speed, well, 3 if you count off, so low speed, high speed, and off. That was the aeration control. So it was manual adjustment. We decided, talking together, well, let's turn this into a septic zone for phosphorus removal. And I'll get into the details of that in a future webinar. So if we're going to do that, then we needed to do the ammonia and nitrate removal in the main body of the ditch. So they put a variable frequency drive so they could control the speed enough to keep good ammonia removal in this aerobic run. So there's a DO probe, dissolved oxygen probe, right around here. And they set a target. Of course, that then could control the speed of the variable frequency drive. And the idea was to make it aerobic enough, watch your ammonia removal, but drop that setting ever so slowly so that eventually you'll get to a point where this part of the ditch is anoxic, oxygen deficient enough to promote nitrate removal. Then you can get the total nitrogen removal in the ditch and then manipulate what's going on in this zone and make it ever more septic for the phosphorus removal. Well, they did that. They had success. What they did was they changed their DO setting. They had to invest in a variable frequency drive, get their control system so that this DO probe here was actually controlling it. And then they would change their DO target by 0.1 or maybe every week or 2 and just kept lowering it, monitoring their ammonia, making sure they maintained ammonia compliance. And then they started getting their nitrate removal in this part of the ditch. Then they closed this gate down so that there was less of this somewhat aerated wastewater flowing into this anoxic zone. Of course, that increased the hydraulic retention time in here. This is a vertical shaft mixer. Of course, it's designed to run 24/7 and keep everything mixed. They now run it for 15 minutes a day, 15 minutes a day. So we've got an energy savings on this aeration rotor. We got an energy savings, maybe not a huge one, but one that's used to run a mixer 24/7, now it's just running a quarter hour a day. On purpose, got some stratification, sludge settling, and then that 15 minutes resuspends that sludge. So it became more septic, particularly in the bottom layer, and that created the conditions that I'll get into in more detail for volatile fatty acid production, create the candy, the septic food source, and then the phosphorus removing organisms that are in the return sludge and whatever leaked through that gate, also in septic conditions, would eat that volatile fatty acids, get energized, and then as they made their way out the gate, marching through the gate, and hit aerobic conditions, then they would multiply. And as the phosphorus, PAOs, phosphate accumulating organisms, BioP bugs, I like to call them, as the critters that remove phosphorus biologically, they would multiply and pull the phosphorus out of solution. And then the phosphorus concentrates in their body and it's removed as waste sludge. So there we go, that turned more septic, at least in the bottom layers. And the tool for that's this ORP. We'll talk about that as an instrument that I'm a big fan of. And I think I got Nick and Ryan on board, and maybe they were on board before that, joining me on that. So here's a picture of James Gaunt right at the outlet. You can see this is where the wastewater leaves the ditch, and that's where the DO probe is that controls the aeration speed. Here's how fast it happened. So in March of 2020, I made the first visit. At that time, you know, these are not bad numbers. Total nitrogen of 10, that's almost where we're trying to get to. And phosphorus was 2. We'd like to see it at 1. So I had to cut the phosphorus in half. They're going to meet that target. So the very next month, this is, you know, a can-do kind of staff. The very next month, they turned things off and they stepped up their monitoring. Didn't see any changes. By May, they were frustrated. Okay, here we're doing all this extra testing. We made these changes. Nothing's changed. Next month, changed their drive unit on their aeration rotor so they could now span over a long, you know, dial in how fast that aerator operates in response to the dissolved oxygen, and then spent 3 months finding the sweet spot. What dissolved oxygen target provided them with that aerobic zone and anoxic zone? They hit it. They had purchased an in-house spectrophotometer. Those things are not cheap. There's another $5 grand right there, maybe more. And look, their phosphorus now is dropping. It's cut in half. They're happy. So it was fun. So I made my second visit and got to celebrate with them. Nitrogen is also now fallen below the 10 milligrams per liter. Phosphorus now not just 1 month, now the rolling average, which is the number by June of the following year. And by August, the rolling average in phosphorus was down around 0.5. They spent something up to $50,000 in all of this instrumentation and controls at the plant. They're getting ongoing electrical savings. If they've quantified it, I don't know what those numbers are. If there's anybody from Great Bend listening in and you know those numbers, want to share them, that'd be great. Pretty interesting on that follow-up visit. It really was a celebration, and the city has an in-house engineer, head of their engineering department, and she came to the treatment plant to talk about what their plans were had this not worked for them. And she said, our estimate was we were going to be spending $6 million, and we just figured it was a necessity and we would have proceeded with that. Phosphorus is now bouncing around between 1/2 part and 3/4. It was over 2. Nitrogen's now bouncing around 6 to 7 and was 10 to 12. So here's some graphs. There's nitrogen. You can see it's pretty interesting. There was a period here where nitrogen was pretty low. And what I learned was they had a very experienced operator who kind of took the information, his knowledge with him when he retired and left. But clearly was doing a pretty good job with nitrogen removal. That climbed up a little bit. And now, even though basically taken away that entire zone that's designed for the nitrate removal, getting better nitrogen removal than the plant had been getting. And here's the phosphorus removal. And this, I think, really over here to the right, and I got to tell you, on my screen, when I'm looking at this is where I've got boxes over here, but over in this right end over here, you can see some bouncing around. And this is where this rolling 12-month average is really I think, helpful for you, us as operators. The state is going to be putting limits on rolling 12-month averages pounds. This is concentration. Kind of hard to translate pounds from one plant to another, so I like to use the concentration for illustration. But you can have your really good months, okay, that one's 0.1 or 0.2, and then your not so good months, that one's about 1.3. But if you're averaging 12 months, you can have the ups and downs and still maintain compliance. All right, finally, nitrogen removal. I think I explained that, and that anoxic zone was converted to a fermenter with a phosphorus uptake and final removal in the ditch. The phosphorus actually goes into the mixed liquor and is removed as waste sludge. There's the cover. This guy on the cover has nothing to do with Great Bend, but that was the magazine that it appeared in. I think that was December. I can't read it. Oh no, June of, I can't read that date. It's right over there. But if you Google it, you'll find the article, and it's encourage you to do so. Any questions or comments, Nick? Has anybody said anything in the chat page on that I ought to?
Yeah, we do have one. The city of Topeka is asking what they landed on for a DO sweet spot.
Yeah, honestly, I don't know. If there's anybody from Great Bend and can tell us, please do. I don't know. I do know that they were, just as I said, moving it very slowly, like maybe 0.1, would drop it, hold it for a week or two, and then drop it. And it was interesting too, because if you notice that timeline, by the time they really got it in place was in the fall. And of course, in the fall, your ammonia limits for most plants around the state are going to be less restrictive. So it turned out really nice to start working on this mid-late summer, and then with their more restrictive ammonia limits. And then as they got less restrictive in the fall, then they could keep really ratcheting it. And then by the next spring, have many months experience. And if that ammonia started to climb, then they could adjust that as they came out of the winter into the more restrictive. Sorry, I don't have the answer. Anything else?
That's the only question I'm seeing.
Okay.
Oh, right. One more. Asking what is the ideal ORP reading for an anaerobic zone?
Yeah, that's a great question. Okay, so I will get more into that, but for an anaerobic zone, I like to see it at minus 200 millivolts or more negative. And it depends upon the water chemistry. If there's a lot of sulfur, it'll get kind of stinky. It gets more than minus 200. If there's not a lot of sulfur, there's a plant in Connecticut that operates at minus 400. But I like to see it at minus 200 or more for that anaerobic or fermentive zone. All right. I could do, well, let me do Parsons. Parsons just fascinates me. This was when I pulled in, I came into Parsons by myself, and this was a few years ago. And in advance, I compiled data and I downloaded the data, and the data Parsons was just fantastic, great numbers. And I thought, why am I here? And what it turned out is I was there to learn. And as I learned, I think the plant staff learned a little bit too, because together we figured out why they were getting such good numbers. It was because of as much happenstance as intentional, at least on the phosphorus. All right, so Parsons, the fellow now is Jake Walker, who's the superintendent there. At the time, I met with Brian Thompson and Kent Drummond. who are the operators. The heart of the beast over here is a Schreiber unit. Those of you who are not familiar with Schreiber units, they call them on their website continuously, the SBR, continuously something reactor, cycling reactor, batch reactor, continuous something reactors. So they're like an SBR, except not really. So here's what they do. This arm here, catwalk, goes around in a circle. There's a rubber tire on the bottom, and suspended from it on this donuts part of it, this is an aeration basin, and in the middle is a clarifier, a final clarifier. So there'd be a headworks. After the headworks, the flow and the return sludge come into this donut. This arm goes around in a circle, clockwise or counterclockwise, I'm not sure, I can't remember, but it goes around, it's about 2.5 minutes to go around. So that's a fairly comfortable walking pace, is how fast it goes around. Suspended from this catwalk is an aeration header with diffusers. So every 2.5 minutes, it passes by the same point again, and it's programmed to cycle on for a period of time to create aerobic conditions, and then cycle off for a period of time to create anoxic conditions. So it's designed to remove nitrogen. And remove nitrogen, well, it does. It's as most SBRs do, once you dial in those air on and air off times. We have some abandoned tankage over here. Let me see, do I have the next? Yeah. We have abandoned trickling filters, abandoned tankage. Not even sure what, more abandoned tank, a lot of abandoned tankage. And then over here, we have 3 aerobic digesters. And you can see by the size of the vehicles here, they're a pretty good distance away. So 3, and they're big, 3 aerobic digesters. And these 2 especially are pretty tall. They're almost silo-like. These are aerated as well with timers as well, but the timers are in no way connected to the timers on the 2 Schreiber units. So the air comes on and off, on for a few hours and off for several hours, totally unrelated to when the air comes on and off in the ditch. Sludge is wasted into one of the aerobic digesters on a timer. So there's a timer that pumps a certain volume of waste sludge over to one of the digesters. And then here's the unique thing. As with many aerobic digesters, there's telescoping valves. But in Parsons, they operate with the telescoping valves pretty much fixed. They don't raise and lower the telescoping valves. So sometimes when sludge is wasted into one of the aerobic digesters, the aerobic digester is aerating, and a gallon in and a gallon right back out again. Other times when they waste, it's not mixing, and a gallon in, and then a gallon of supernate comes out. Now, the supernate in aerobic digesters has a lot of phosphorus in it, a lot of ammonia that release during the digestion process. However, if you cycle the air on and off so that it goes septic, you create an environment that facilitates this phosphorus, creates the food source. The waste sludge has organisms in it. They'll eat the food source. And if it's aerating, it's mixed, you're blowing some of these energized critters back into the aeration basin. And because of that, they've created side stream fermenters for phosphorus removal. These 3 aerobic digesters, because they go aerobic and septic, when the air's off, they're not mixed. I failed to mention that. When the air's off, they're not being mixed. So the blanket settles, is that deep in the blanket, it goes anoxic, anaerobic, goes septic pretty fast. So 3, 4, 5 hours, you've got nice septic conditions, creates this food source, and then the volatile fatty acids, and then the phosphorus removing organisms have their fill, and they become energized. And if you only were to pull the supernate out, you would have these energized organisms that would eventually be hauled off site. But because they aerate it while they're wasting from the Schreiber unit, they're bringing some of those energized organisms back in. And in the aeration basin, they're removing phosphorus. Quite good nitrogen removal. In fact, anything's getting better over the years. Look at this 5 milligram per liter kind of number. But look at the phosphorus. I changed the scale over here. So there's a 1. Something happened here. They had a bad number. But typically 0.25 is the rolling average. And once again, I like this graph because it shows they had what for them was a bad number. I forgot how high that went. It goes up a little ways. That 1 month stuck around in the average until that month finally dropped off. And then they're back down. Look at that, way below 0.25. Quite a story in Parsons. Any questions or comments on that? We have about 15 minutes left, or not even, so I'll either run through another one real fast or we'll drag this out with some discussion.
Yeah, just a comment. Looks like Norton is telling us that Schreiber calls them counter current aeration basins.
Okay. Yeah, I think they call them CSRs. Something continuously sequencing reactors, what they call them on their website. Now it's a Parsons product. All right. I got 2 left. One's an SBR. I think I'm going to skip the SBR and let's go to an Aeromod. Pretty interesting story. St. Mary's. This is one that things didn't work out so well. So, and it was not Mike DeCipio's fault, and it was not the fault of the support that Aeromod's Ben Choka provided. It's Grant Weaver's fault. So those of you who have Aeromods, you're familiar with the design of them. This is the anaerobic zone coming down this channel. This would be the fermenter. What do they call it? Something in fermenter. Can't remember the other word. So the flow comes, these 2 basins are the aerobic digesters. So the influent goes right through them. They're not connected to the mainstream flow. Flow goes through the fermenter, and then it goes to one side, and you can see this side's being aerated, well, this side's not. Then it goes to the other side, and then the clarifiers are here. And then the skimmings and the sludge are airlifted, and they pour into this fermenter zone. The flow is split here, so half of it goes around this way, and the other half goes around this way. And you can see, well, this one's being aerated, that one's not. Well, that one's being aerated, this one's not. And then these are the clarifiers. If you're not familiar with an aeromod, you're probably totally lost, and I apologize for that. Well, my observation has been that aeromods are good, not fantastic, but good at nitrogen removal, and they're reliable at nitrogen removal. And another observation is aeromod is working very hard with every new treatment plant to make it a little better. So very few of them are exactly the same because they're always trying to make them a little better. And right, the last, maybe they've got it, but they're working on trying to dial in this phosphorus removal. And what happens is, because an aeromod has no moving parts in the clarifier below water, which is a really neat feature, and because they use airlift pumps, there's an awful lot of high DO flow and the skimmers coming into this fermentive zone. So the idea of working with Mike's a plumber, licensed plumber. So he put in all kinds of neat piping to take this flow coming out of the clarifier to bypass and to shoot it, bypass this fermentive zone and to shoot that flow into the more aerobic zones. The idea was, let's make this more septic. Horton plant that Nick talked about, their effort was to provide less mixing in this tank. Instead of 24/7, it was an hour on, hour off. Here it was, let's try to get all of this high DO waste out. Well, it worked in that it made this zone more septic, which then the phosphorus did drop for a few months. However, there was so much back pressure on the airlift pumps that the sludge blanket rose in the clarifiers to the point where there was a lot of ammonia release, and he actually violated his ammonia, I think, even for a couple months. So all of that got ripped out, and now there's a new plan to use this zone in the back to dump some mixed liquor in there and use that as a side stream fermenter, much like the Parsons story that I talked about. So initial plan was, let's make this zone more septic by diverting the RAS and the skimmings, and there's a lot of skimmings in an aeromod because there's no scraper in the bottom, so they have a lot of float. And so to remove that, they have very aggressive skimming, which of course with the airlift is high dissolved oxygen. So it's got that high dissolved oxygen water out of the fermentive zone. It did boost the fermentive zone, but there was too much piping involved. So those airlift pumps were not pumping anywhere near as many gallons per minute, which meant the sludge blankets built up, and they built up over a couple months in here, ever so slowly, and until they started releasing ammonia. And then to fix it, had to take this equipment, the piping, and divert it back where it was originally designed. Here's the results here. This, I don't remember. Let me look at the phosphorus one. So here's where the phosphorus really was down below the 1 for 4 months in a row. But after that, after that period, see, the nitrogen was climbing, and it's too bad I don't have a breakdown. More of it climbing was ammonia than nitrate. Typically in an aeromod, ammonia is like non-detect, and other than a little bit of organic, pretty much all of the nitrogen is nitrate. So here, actually, this climb was an ammonia spike. This one happened because the operator got in a motorcycle accident, and the one-man operation, and the town kind of struggled until Mike was able to get back on the job. So lesson learned there is if that zone could be made more septic, everything's in play. So for other aeromods, there are now in the design, a lot of the flow is shooting past their fermenting zone. Those of you have aeromods of the newer version, some of you actually have channels where some, if not all, of the flow is skimmers, and return sludge is bypassing that fermenting zone. I think a little bit of it goes into it so it can seed that zone with the phosphorus removing organisms. And then the long-term strategy here, next step, Mike's and Ben Jilka of Aeromod, the three of us thought, well, we could take some waste sludge, sit it in here for a period of a week or so, let it go septic, and then pump it just right back into the main body of the ditch. And that should be a supplemental phosphorus removal concept. All right, that pretty much does that. Is any questions or comments on the St. Mary, the Aeromod situation? No. Okay. Well, I think we're pretty much at the end. Unless somebody has something that you'd like to put out there for Nick, Ryan, or myself, or to talk amongst yourselves. Other than that, I can give you an overview of what's coming up. Nick, go ahead.
Yeah, there's no further questions. I'll let Grant cover the remaining webinar series.
So next week is off. Happy Thanksgiving, everyone. Then the week after, I'll do nitrogen removal. And then we'll close out the series with the phosphorus, and then kind of the big picture review. Now, the phosphorus one on December 6th, I'll be doing that. I'm doing that solo. Nick has got another commitment. And Nick has that great experience with the chemical phosphorus. So I think what Nick and I have discussed is I will, on the 6th, I'll do biological. And then on the 13th, he'll spend some period of time talking a little bit about chemical phosphorus removal. So next weekend, no webinar. The week after, I'll use my in the toolbox nitrogen removal presentation, and then my in the toolbox phosphorus removal. Nick then will add to the phosphorus by talking about the chemical, and do an overview of the whole thing, and whatever discussion, anything anybody wants to talk about or have us discuss, and maybe we'll get into some of that cohort discussion as well. And with that, on behalf of Ryan, Nick, and myself, I thank you, and I look forward to seeing as many of you as possible in 2 weeks.